Okay, here's a German word for you. Sitzpinkler. Go on, take a second. What do you think it means? It's one of those amazing, super specific words that tells a whole story in just one go.
So, how close did you get? Literally, a Sitzpinkler is someone who pees sitting down, but it's actually used to mean something more like wimp. And even that doesn't quite capture it. You see, the word got popular on a comedy show, so it's this kind of light-hearted jab about changing ideas of masculinity. If a translator just swaps it for wimp, you lose all of that rich cultural backstory. And that right there perfectly shows the core problem with translation. It's an almost impossible task.
And that impossible task is exactly what we're going to dig into today. We're going to follow the incredible journey of how we taught computers to do something that, let's be honest, even we humans find incredibly hard.
Okay, so to get why machine translation is so tricky, you first have to understand this one big problem that every translator faces, whether they're human or not. It's this constant tug of war, right? Between getting the meaning exactly right and making it sound like a normal person actually said it. So this whole dilemma really comes down to two big ideas. First, you've got what's called adequacy. This is all about keeping the exact meaning. Super important for things like legal contracts or instruction manuals, right? You can't mess that up. But on the other side, you've got fluency. This is about making it sound smooth and natural, like a native speaker wrote it. Think poetry, song lyrics, or marketing slogans. Now here's the catch. A translation that's perfectly adequate can sound really robotic and clunky. And a translation that's perfectly fluent, well, it might actually stray a little too far from the original meaning. So, when the early pioneers of AI first took a crack at this, what was their big idea? Well, their first approach was all about rules, and I mean tons and tons of handcrafted rules. You know, the history here is a real roller coaster. Back in the 50s, everyone was super optimistic, but then this big report came out in 1966 that just slammed the whole field. It basically said machine translation was too slow, too inaccurate, and way too expensive. And that killed most of the research for over a decade. For years after that, the main strategy was to build these enormous hand-coded dictionaries and grammar rulebooks. But then, in the 90s, everything changed. A totally new idea came along: statistical machine translation. The thinking was, forget teaching the computer grammar rules. Instead, let's just feed it a mountain of already translated texts and let it figure out the patterns for itself, just based on pure probability. Now, this statistical approach, it was a massive leap forward, but it still had one major weakness. At the end of the day, it was really just matching chunks of text. To get to the next level, machines needed a completely new way to think about language.
And that's where the real game changer comes in: neural machine translation, or NMT. See, NMT doesn't just swap words. It actually tries to understand the entire meaning of a sentence as a whole, and then it generates a completely new sentence from scratch to express that same idea. It's a huge shift. We're going from just matching phrases to actually trying to grasp the meaning.
So how in the world does that actually work? Well, the core idea is something called an encoder-decoder model. It's a two-step process. First, you have one neural network, the encoder, that reads the whole sentence you want to translate. Then, and this is the cool part, it squishes down the full meaning of that sentence into a list of numbers. It's a mathematical representation of the idea, sometimes called a thought vector. Finally, a second neural network, the decoder, takes that thought vector and uses it as a blueprint to write a brand new sentence word by word in the new language. It's kind of like if you read a paragraph, closed the book, and then tried to explain the main point in your own words. This whole encoder-decoder thing was pretty brilliant, but it had one big flaw. When it came to long sentences, that thought vector had to cram so much information into one little package. It would often forget what the beginning of the sentence was about by the time it got to the end. The solution to that problem was a major breakthrough called the attention mechanism. And this is what that attention actually looks like. Basically, as the decoder is writing each new word, it's allowed to look back at the original sentence and pay attention to the most important words for what it's trying to say right now. So when it's about to write the word relations, you can see it's putting 89% of its focus on the German word Beziehungen. When it gets to Obama, boom, 96% focus on Obama. It's pretty amazing, right? It's like it's mimicking how a human translator's eyes would jump back and forth between the two versions of the text. So with breakthroughs like this, NMT has gotten incredibly good. I mean, it's powerful, but it is far from perfect. And honestly, looking at where it fails is actually pretty revealing.
Yeah, NMT has some pretty big blind spots.
For instance, if you train a model on dense legal documents, it's going to be terrible at translating movie subtitles. It's also really data hungry, so it struggles with languages that don't have billions of words of translated text available online. It's not great with rare words either. And if you feed it messy, low-quality training data, the performance just falls off a cliff. But maybe the most interesting weakness of all is something researchers call the fluent fool problem.
And there's this one really wild example of this. A neural network was trained entirely on the text of the Quran. When researchers asked it to translate a simple phrase, "look around you," the model came back with, "take heed of your own souls." I mean, think about that. The sentence is perfectly fluent. The grammar is flawless. But the meaning is completely, utterly wrong. That's a fluent fool. It's basically hallucinating an answer based on the statistical patterns in the religious text it was trained on.
And that really gets to the heart of it all, doesn't it? Neural machine translation has become this incredible pattern-matching machine. It can learn the relationships between words on a scale we can barely imagine, but it does all of this without any real understanding of the world. It doesn't know what a riverbank is versus a financial bank, it just knows the patterns of the words. So the big question we're left with is, will that always be its limit?